introduce the idea of VLSI design, that history of IC design. Now, if we summarize that previous lecture, mainly what we have discussed, that is the digital design trend. So, digital design trend the current trend the first thing, the first important thing is that CAD tools are introduced. CAD tools are introduced in the process due to the increased size and complexity of ICs. The next is that to standardize the design procedure. Earlier, normally the designer, they used to do that thing based on their own requirement. So, some designers want to standardize the design procedure. Last day we have discussed, this is mainly nothing but the design flow. That means, starting from the specification of the system or the problem specification, you can tell how we get the circuit to be synthesized on one piece of silicon, that we have defined as the digital design flow. Next is the development of CAD tools. Actually, the first point was that CAD tools development. Here, this CAD tool using the HDL. It means the development, better we call the development of some hardware description language, we call HDL, which is the input of the CAD tools. And actually the mixed of these three is the an HDL based design. And which contains this HDL based design, and that every steps we are going from the upper level hardware to lower level hardware. Starting from that problem specification, we are giving that HDL code, that means hardware representation, uh, code representation of an hardware piece. Then we are using that synthesis. So, it is synthesized to some circuit. Then we are that circuit we are partitioning, and then how it is placed, each module we are calling that floor planning or and placement. Then how these modules are interconnected, we are calling routing, and each step on each of these phases actually we are going nearer to the hardware. So, that is why sometimes it is called that this design flow, VLSI design flow, is nothing but that more and more hardware, and which is approaching to the piece of silicon. So, this is design flow. So, today our topic is that hierarchical design and the regular and modular structure. Starting before starting that hierarchical design, first I want to tell the behavioral design or behavioral representation of a design. Behavioral representation. Behavior is a very simple term, that if we consider that my system or the problem is a black box, then for a particular set of inputs, how this system behaves, that means what is the output. So, for a given set of inputs, what is the output? If I know that thing, assuming that my system is a black box, then that is a behavioral representation. So, behavior may be specified by behavior can be Boolean equations. Boolean tables of inputs and outputs. Algorithms written in some HDL. So, first we see that how behavior is represented by Boolean equations. Now, we are taking one example, that 1 and 1 bit adder. Now, what are the inputs? What are the inputs of adder? This is the two operands, A and B, say a carry input, C, a carry output, say C out, a sum output, say sum. Now, here this is a black box and the inputs are 3 ABC, outputs are C out and sum. So, always the C out and sum can be represented by A, B and C. Now, what is that expression of C out and sum? Say C out is nothing but AB plus BC plus CA. Similarly, sum is you give sum is ABC plus A bar B bar C plus A B bar C bar plus A bar B C bar. So, this is the two Boolean equations that always we can represent, and this is nothing but the behavioral representation of 1-bit adder. Now, if it is represented by some hardware description language, so this an algorithmic description of carry, an algorithmic description of carry. Now, I am writing that module carry and Cout ABC. Cout is the output and ABC are the inputs of the module. Then Cout is defined as output line and ABC are defined as the input line. Just like our software program, we use that integer, float. Similarly, here only input and output that are defined. Now, this output expression of Cout is nothing but AB plus AC plus BC, and I am assigning this term to Cout. This is the module of carry. So, this is one piece of hardware description language, HDL code. This is similar to Verilog code. Similarly, again this is a module of carry, but one new thing I have introduced, that is the timing behavior. Say all of we know that delay is one important factor in any circuits. So, now this carry module, it is embedded in some circuits, and if I want that these outputs should be activated at some point of time, then I am using say some where type, where hash 20 means at the 20th time units, or say clock, say what is that system clock, based on that Cout will be activated. That means I will get the Cout as AB plus BC plus AC at 20th clock. Okay. Otherwise, all are same. So, this is some HDL input. Now, the same thing I can present as a table form. These are all the different ways that I can give the inputs, or how I can represent my system. So, this is a Boolean behavioral specification for Cout. We know this, we know the expression of Cout, AB plus AC plus BC. Similarly, I have defined my Cout as output line and ABC are the input lines. Now, I am giving this thing as a table form. See, this is nothing but the truth table we know. These are the ABC are the inputs, ABC are the inputs, and Cout is the output. And this is AB plus AC plus BC. When these inputs are 1, only that time I am getting my output 1. And these are don't cares. Question mark means don't care and all. So, these are nothing but the truth table, one simple truth table. We can give these as an input. This is a very easy way to give to feed a system.
So, while writing a program, we can just format a field. This is a program.
This is not a program. This is a representation, that you want to find out that expression, say C out is AB plus AC plus BC. So, somehow you have to give that as a, you have to represent that thing. I am representing this thing as a table, as a truth table. Actually, here table means truth table.
Madam, that
So, automatically this thing will be synthesized.
the primitive carrying is a module type.
This is a module type. Normally we use module, but you can use that primitive also. Now, another thing is a structural representation. Structural so, how we define? We can define that how components are interconnected to perform a certain function. Or what just now we have told, a behavior or represent a behavior. Represent a behavior. Now, the different level of abstraction, first we have discussed that thing, level of abstraction is module level, it can be gate level, it can be switch level, it can be circuit level. So, we have seen the different ways we can give the system inputs. Now, we come to that point, what we want to discuss, that hierarchical design structure. Now, we take one example. Here we have taken one example of 4-bit adder. Now, what do we mean by hierarchy? So, given a big system to be designed, the approach is nothing but our software approach, just divide and conquer. So, here one big module or big design is partitioned into some sub-modules, and then again that sub-modules can be broken into some sub-modules until that module is small enough to be managed, to feed as a or to represent as an HDL code or to be synthesized by our CAD tools. So, this is a very small example. This is a 4-bit adder. Now, I have partitioned this thing as a 1-bit adder. So, 4 1-bit adder at the second level. Already one 1-bit adder, that two outputs, that sum output and carry output, we have written in 3 different ways. So, this is given that carry and sum, and each carry and sum is nothing but some expression of AND OR. So, what we will do? So, only one 1-bit adder, module of 1-bit adder will write, and then we will replicate that thing. Now, again this is the same idea is that regular and modular structure. So, regularity means regular and see here 4-bit adder, the same 1-bit adder that is duplicated. So, if you increase that number 4, only you will extend the same module and you will repeat that modules. So, this is a very regular thing. Modular means, see that 1-bit adder, and I can treat that thing as a module, either the full 1-bit adder, that is a higher level module, or that 1-bit adder, output of 1-bit adder, that can be 2 small modules, one is carry module and one is sum module. In our earlier example, we have shown that carry is a small module and sum is another module. So, this is a modular structure. What is that advantage? Why the VLSI people always goes to this type of design? Because that in that silicon, if it is a repetitive type of structure, then thousands or lakhs of modules we can easily design on the silicon. Ultimately, we will discuss later that this is nothing but when the design after simulation, the designer will give the output of some mask information. That means, where and what type of transistors to be formed on the silicon. This is the ultimate information will go to the fabrication people. So, if it is a repetitive type of structure, that means regular and modular structure, then it will be very advantageous. That is why this is one of the important aim of the design. Always we will keep this thing in mind. Now, this is a structural representation. Now, we know that how 4-bit adder has been represented. We know that paper design. So, if you write that thing HTL code, then module 4-bit adder, sum is the output. Similarly, C4 is the output, sum and C4 is the output, whereas A, B are the 2 primary inputs and one C in means carry in. So, input output are defined. Now, see that C out is defined as a where and it is of 3 bits 220, just like our array is defined in software. So, now one module 1-bit adder, I am giving this as the name A0. So, this is the output, C out 0 is the output of A0 and this is sum 0, A0, B0 are the 2 primary inputs and 1 carry in. So, A, B, C, these are the 3 inputs and these are the 2 outputs, carry and sum of 1-bit adder. See that picture, this is one 1-bit adder, carry and sum, just we concentrate on only one module. So, carry is represented, this is A0, so this is my A0, this is my A1, this is A2, this is A3, and now these A0, A1, A2, A3 are represented like that, and these are the module end. Concept is just like our function call in software. Again, module 1-bit adder. So, C out sum ABC, input is ABC, output is sum and C out. Now I am giving sum S1 is sum ABC, carry C1 is C out ABC, and this is the N module. There are many other ways you can represent. This is the trivial ways that just I have started from the scratch, that if someone does not know that he has no idea of that HDL code, that he can, but he has some concept of software programming, then he can start from here. Then module carry C out ABC, input output is ABC output. Now you see, if you see that thing, and G1 XAB, what is that thing? See, XYZ is nothing but some word type. So, X is AB, and that means in my HDL code AND is defined. Similarly, Y is AC, Z is BC, and G4 is nothing but OR of XYZ, and X is AB, Y is BC, sorry, Y is AC, Z is BC. So, this is AB plus AC plus BC, and that gives you the carry. So, this is one carry module. So, this is the structural representation. The first one I have told, that is a behavioral representation. That means, because that it varies from designer to designer. If one designer is expert enough, he has enough idea that how the design can be represented. Let me say one adder. One people can simply tell that carry is AB plus AC plus BC. But another designer, he may optimize that thing. So, he will give the gate level representation, and another someone may give only that behavioral level description. This is similarly for a big system, sometimes one designer can represent that thing only using the block diagram level. He does not know that what this we are taking one example of image compression. Now, image compression, there are several algorithms exist. Now, one algorithm, how the algorithm will be implemented, that always I can represent by block diagram level. Now, some other person, he is expert enough that he may know that how this block diagram level can be represented so that it can be designed efficiently. He can optimize the thing, or he can take the how fast it can be designed. So, what he will do? He will come to another level down, and he may represent that thing by some circuit level or gate level, just like AND OR level, and then he will do that thing. That is why different type of representation, behavioral, structural or table form, and if one person is enough expert, he may knows that what will be the truth table, that what is the function of that thing, he can give in that level itself. Or sometimes say from other programs, that output I want to feed, particularly for testing purposes, I may feed that these are the given test sets I want to feed in my circuit or design. Then obviously it will be very helpful if I use that table form, that these are the inputs and this is the outputs. Probably I have generated by software. I know that this thing, if these are the inputs, it will be the correct output. So, these are the different forms that I can give. Now, last day we have given a simpler uh, digital flow, the digital design flow, and this is again the same thing. Now, we have some more idea about the design entry. So, this design entry, just now what we have discussed, these are the different ways of design entry. So, you can tell this can be some HDL code. This can be some structural representation, again coded in HDL, because ultimately that should be the thing. I am giving that HDL. Then logic synthesis. So that means what will be the output? We know that this is a circuit, a synthesized circuit. We can tell that this is nothing but net list. That means which component is connected to what. Then partitioning and floor planning, actually in real life we call these are the logical design or the front end of CAD. So these CAD tools are available. We call the front end CAD, and normally we use that synopsis CAD tools here. Now this, once I got that full circuit, first I partition that thing as a module, because now we have the idea of hierarchical design or the modular design. So how these modules can be partitioned. Then floor planning. We have that idea that how much area I can give, or what is my requirement to get the chip, the size of the chip. Based on that, I will do this floor planning. Then how these modules, one step before when it was partitioned, that how these modules are placed, and this is called that placement. And then how these modules are connected. Several algorithms available for this placement, routing and partitioning. Nowadays the trend is we do the placement and routing together, because if you think, actually all are NP complete problem. So once I placed or the placement is over and then I start routing, then it may happen that the final design I will get, that may not be optimum. So nowadays some other algorithms are available and placement and routing is done parallelly. Now we see that what we are doing in the left hand side. See here, this is some pre-layout simulation. Pre-layout simulation. Our concept is just like, first I given a problem, first I represent that thing in some HDL code, then I will test by simulation whether that given this input it is achieving my required output or not. Again logic synthesis, circuit is synthesized, I will test whether my synthesized circuit is giving the correct output or not. So the same thing is doing. So this is the simulation, pre-layout simulation, and if it is not achieving that thing, again I am changing the thing. And this is same actually for these two steps, these two part is same. After partitioning also I can do that thing. Now this floor planning, placement and routing, we call this is the back end of the design or physical design automation, and CAD tools are available for that. What we do, some circuit extraction, that means after routing this thing, again the circuit which gives you that output or that behavior you have fed earlier, that thing is extracted and simulated. That means whether it is giving that same output or not. This thing is very important, that post layout simulation, because after layout it will go for that fabrication. So this post layout simulation is very important, and then if it does not achieve the goal, then again it will be changed. And on each of these steps, if you see that starting from that HDL code, you can think that this is a soft code or the representation, soft representation of my hardware, and more I am going to the hardware level. That's why it is called the digital design flow is nothing but approaches to the silicon. So, silicon is actual hardware, and more we are going to that hardware using the CAD tools. Okay. So, here we stopped our introductory portions. Now, I want to give some idea about the different type of design methodology. Nowadays, that what VLSI design methodology are used. So, sometimes we call these are the VLSI design styles. The first one is the programmable logic devices. Short we call the TLDs. Then gate arrays, called GA. Standard cell based design, sometimes we call that semi custom design, and this is full custom design. So, first we see the programmable logic devices, the PLDs. So, we can divide that logic families, PLD logic families, as standard logic, and these are ASIC. Now, standard logics are divided as programmable logic devices or PLDs, then gate arrays, then cell based designed, cell based, and full custom. Now, first thing is that PLDs we called SPLD means simple programmable logic device. S means simple. Simple programmable logic devices. Similarly, CPLD means complex programmable logic devices, and the most important one is the FPGA, the field programmable gate array. And nowadays FPGA is very important. So, in this class we will just give a quick view of that FPGA, because this is a very important design style nowadays.
Those PLDs extra come under standard logic or ASIC?
This is standard logic. What was your question?
Whether PLDs, GA, etc. come under standard logic or ASIC?
This PLD, GA, cell based, full custom, these are all ASIC type. ASIC. Standard logic is one that is simple circuit. If we start from a scratch, that just AND all level circuit design, that should be our standard logic. Just that some synthesized circuit. This is that ASIC. This is form of ASIC. So, first we discuss that FPGA. So, see this this is a regular array of cells. FPGA is a regular array of cells and arranged in a two-dimensional order. And CPLD, these are complex programmable logic devices. Normally they are arranged in this way. These are the cells and this is the space for interconnection. And here that FPGA, that these are the logic cells, and the space row wise as well as column wise I can do the connection. I am giving a detailed picture. Now, what is the difference of CPLD and FPGAs? I am not telling that SPLD, because that was the initially it was evolved and nowadays it is not being used, because they are simple programmable logic device. But the concept is that thing, that some logic cells are already inbuilt and then you interconnect based on your requirement. That is the concept. So, here architecture was, so architecture, they are more combinational. These CPLDs are more whereas these are more registers plus some RAM. That means memories are there. This is a very novel idea of FPGAs, that RAMs are there. That means all circuits, that lookup tables of all circuits are stored there and it is interconnected. I am giving later that picture. Then density, that logic gates are of 0.5 to 10K, that type of logic gates were there. It is here, it is the order is 1K to 500K. Performance is normally nowadays it is 200 megahertz, and FPGA depends on the application. Normally it is up to 135 megahertz, that type of thing. And interconnects, normally it is a crossbar type of thing, and these are called incremental means that every cell can be interconnected to everyone. Now, this is a detailed picture of a FPGA architecture. This is a FPGA architecture. So, these are, we call that configurable logic blocks. These cells, that the cells are arranged in 2D order, these cells are, some logic blocks were placed, and in between these are some programmable interconnect. That is why it has been written incremental, because any cell can be connected to any one, and you see the row as well as the columns we can use, and they are programmable. From outside we can program that thing. And nowadays that FPGAs are available, that IO blocks are also programmable. So, not only the cells, not only the interconnects, but these IO pads, see the boundary, in this boundary that small cells are there and they are IO cells, and these IO cells are also, these IO blocks are also programmable. So, mainly we can think that FPGA, it consists of some configurable logic blocks, CLBs, then programmable interconnects and programmable IOs. Now, if it is programmable means, you know, this is nothing but a switch, either I can connect or either can disconnect, simple switch. Now, here the concept is, this is an anti-fuse type of thing is normally used. All of us have that idea that this is a one MOS is actually the function of MOS is as a switch. Now, see here, this is a, you know, that silicon dioxide layer, and this is a metal wire, and then again it is a metal. Now, see here, this is a link, this one. So, the concept is, normally what is the concept of fuse? Fuse is normally on when that high voltage comes or that current passes, then it goes out. So, anti-fuse means the concept is reverse. Normally it is off, and when that current comes, then only it passes that thing, that means it links. So, this is the concept, that this is the, in the via stage, this one link is there, and that is why it is called that anti-fuse elements, and it is not reprogrammable, only for one time you can do that thing. That means, if one FPGA is burnt for one application, for one time use only, that is for one application only. So, this is that, and that I told that that CLBs, mainly that memories are there, and these are some SRAM cells, and this uses more space. This is reconfigurable and volatile and requires that PROM. So, more, this is the memory cells are connected. Normally, this is used in any type of FPGAs. Now, what are the configurable logic blocks? That is very, because ultimately the cells are connected. So, configurable logic blocks are 4 input function generators. These are the 4 input function generators, and this is lookup tables, that means RAM or logic functions. See, any, you just think any combinational logic, you can represent that thing as a truth table. These are the inputs and these are the outputs. That is nothing but lookup table, table form. Now this table I have stored in some memory. How that concept of memory is coming? So this 4 input function, I am telling that is my table. That table is stored in a memory. That is the concept is very simple. So here that configurable logic blocks, this configurable logic blocks are nothing but the representation of these memories. Now some registers are there. Remember, I have given that what is the components of FPGA? Some registers, because nowadays these are both combinational as well as sequentials. So each can be configured as flip flop or latch, independent clock polarity, asynchronous and asynchronous set reset. Both are available nowadays. So these are the main components of a CLBs. Now we see one lookup tables, then concept will be clear. Say this is one combinational logic. It has 4 inputs A, B, C, D and 1 output Z. Then this A, B, C, D, Z, just I have given the truth table. Based on that circuitry or the Boolean expression, whatever you tell, then this table is stored in the memory, and whenever needed I will take that as my lookup table, just like input this, if this is the input, what will be the output. So the concept is that. Now these are the 2 important points, that capacity is limited by number of inputs, not complexity. And nowadays that convention is that it is given as a 4 input, all the lookup tables are stored as a 4 input logic. This LUT means lookup table, or as high speed synchronous dual port RAM. Now come to that programmable interconnections. Now these are the CLB blocks. What I told, that interconnections can be done row wise as well as column wise. So this is the switch matrix, and connection can be done from any CLB to another, any other CLBs. So these are the switch matrix kept at the junction, and these are the interconnection path. So from any CLBs, and this box or this switch matrix, actually it will switch from any CLB to any CLB. See, the picture is very simple. That means any type of combinational or sequential logic, first I have represented that thing as a memory, that I have kept as a CLBs memory, and some registers etc. are there. Then what I am doing, some for interconnection, the flexible interconnections, at every junction we have kept some switch box, and then that interconnection is programmable or controlled from outside. So this is the main picture of FPGA. Similarly, that IOs are also programmable. That means that boundaries, that input output cells are also there, and they can also be programmed. Now for FPGAs also, that design entry, the design flows are same as what we have given. So design flow of FPGA. Okay, next day we will start that thing. today we close here that concept of FPGAs.
Great.
ঠিক আছে।